Hello and welcome back to another VMK in the game development series. In this VMK, I will show you how to add a new kind of geometry into our game engine. This geometry is going to be a cylinder. So with the cylinder, we can do some interesting things. We can use it to create columns in a game. We can use it to create things that are sort of cylindrical in shapes, like maybe pop cans or tires even, or anything that sort of has a cylindrical shape. Now, when you think of cylinder, you most likely think of objects that have a circular cross-section and are tall. However, in our definition of a cylinder, it will be any object that has any number of sides, and the number of sides can start from 3 and go up to 20, but you'll see the code and you can manipulate that so it can be higher than 20 if you want it to be. And what we're going to do is basically create a polygon out of these shapes. So for instance, if we take a 3-sided figure, we'll have a triangle, and then we're going to extrude that shape upward to create a cylinder. So if we're using a triangle, we're actually going to create a prism because we'll have like this long triangle shape that's just extruded. Now, if we increase the number of sides for the object, then the quote-unquote cylinder will actually start to become more and more looking like a cylinder that we envision when we say cylinder. So let's get started. Before I go into discussions of how to create the cylinder, there is one thing that I noticed when I was cleaning up some code here from before. If you go and build the existing project, you'll notice that you get the following message. And there's the warning that I was referring to. Okay, so let's go back up here. The warning that we get is from our plane class that we just finished creating in the previous video. And the message we get is no public symbol found, therefore this will be inaccessible. Well, what this means is if we go into our plane class, you'll remember that all of our class itself is defined inside of the .h file. And if we go into the CPP file, which we need to do through here, plain CPP, we don't have any code implemented in here. And remember, the way we fixed that in the other classes, like for instance the general lib, we had to create this dummy function so that the compiler didn't give us those warnings. Well, we can do the same thing here for the class.cpp, but I've already structured the destructor to take its place. So you'll notice here that we created a virtual destructor, but we never implemented it because it has no curly braces here to implement the instance of this destructor. So what we can do is inside the plain.cpp, just down below, implement the destructor. Now the destructor doesn't do anything, so it's just basically empty. But as soon as we put this guy in and now rebuild the project, we won't see that warning message anymore. Here's the math lib, and you can see here it compiled the CPP file, so there's no more warning message. Okay, so now let's get started with this new type of geometry. We're going to implement it as an object inside of the object lib, so we need to go into here and add a CPP and .h file. So again, we're going to go add new item. We'll first add the .h file, and it's going to be called geometry cylinder. And we do that again for the CPP. Okay. Now, before we start implementing code here inside Visual Studio, let's go into PaintShop Pro so I can give you a visual representation of what this class is supposed to be creating. We're going to create a very general class to create any kinds of cylinders. And as I said in the introduction, we're going to allow the user to specify the following. We're going to take in the number of sides that our cylinder is going to contain. We're going to also take in a radius, and we'll also take in the height. Those are the 3 parameters that the user will be able to manipulate through the constructor. Now the number of sides is going to determine how the cross-sectional view of the cylinder is going to look like. So for instance, let's say the user specified 5. That means we're going to be creating a cylinder that has 5 sides, like so. So imagine this being very straight lines, unlike the way that I drew them. And the radius of the cylinder is going to be located from the center point. If we draw a line out to any of these points, this is going to be the size of the radius. So this is going to be radius. This distance here is going to be the radius value. This distance to here, this distance to here, and finally this distance to here. All those are going to be equal to r, which is equal to the radius. Now the distance from the center to here will be a little bit less than r because of the way that this line clips the distance here. So each of these are going to be isosceles triangles, and the distance in between the vertices themselves is not going to be r, but the distances to the vertices is going to be r. Now to make this a cylinder, what we're going to do is extrude this shape vertically. So imagine this all being very straight, and this bottom face of the cylinder itself will also have 5 sides. Let's see if I can draw this. 1, 2, 3, 4, 5, and imagine a line back here. And again, this bottom face is going to have the same deal, where each of these distances to each of these vertices is going to be r. Now the height is going to be defined by the value that the user specifies here. So I'm going to just label that h, and that's going to give us our full cylinder. Now our constructor has to define all the geometry here so that OpenGL knows how to draw it. Now there is a special way that we handle this, and there is a little bit of math involved to generate all these vertices. And when we get into texture coordinates and things like that in the following videos, you'll notice that things might start getting very, very confusing. So it's a good idea to get a handle on how everything is laid out. And I'm going to try to lay it out here in PaintShop Pro. But if you're having difficulties understanding it, just sit down with a piece of paper, draw it out, follow the code step by step, and try to understand what each of the things that you're seeing in code actually represent in the real geometry. Okay, let me just delete this, and I'll redraw a new cylinder. This time I'm going to draw a simpler cylinder with only 4 sides. So again, this cylinder is going to look more like a box or an extruded rectangle, but the way it's defined in the class actually allows it to be a cylinder. So we're going to have a distance from the center out to vertex 1 here. We'll label this V. Well, the first vertex is going to be vertex 0 because everything is going to be 0 based. So I'm going to label this V0. Then working our way counterclockwise, we're going to have vertex number, well, V1, which is the second guy. Then we're going to move over to this side, and this is going to be V2. And lastly, this one over here is going to be V3. You know what? I actually should have drew this a little bit lower on the screen. Let me just go and grab this and move it on the screen to the bottom here. Now, inside our code, what we're going to do is create 2 of these instances. So the bottom one is going to be the bottom cap of the cylinder, and the top one is going to be the top cap of the cylinder. And once we have both of these vertices defined, this is going to be V0, V1, V2, V3, and we're going to have to change the numbering here because these are going to be different vertices. So let's go over, get this tool out, erase these values, and fill them in with the correct values. So we're going to go 0, 1, 2, 3 on the bottom, and then we're going to go 4, 5, 6, 7 at the top. Now remember, we have number of sides equal to 4. So we're going to have 4 on the bottom and 4 on the top. Notice the way that we've numbered these. The one on the far right is always 0. The one on the far right at the top is going to be 0 plus the number of sides. Anytime we refer to the vertices at the top, we always take the value of the vertices at the bottom and add the number of sides to it. So for our case, we're going to be adding 4. You'll notice here this vertex is number 2, and the corresponding one up above is number 6, so 2 plus 4. This one here is 3, 3 plus 4 is 7. They all line up. Now if we were just to draw lines connecting each of these vertices, again, these should be straight lines, then you can see how the cylinder begins to take shape. Okay, so this is what we're going to be creating. Now let's go into the code and start writing the functions to actually get all these vertices lined up properly. We'll begin with the geometry cylinder.h file, and here's what it contains. At the top we have a bunch of includes. We have core.h, geometry.h, plane.h, vector3, vertex 2, and vertex 3. Our class itself is going to inherit from the public geometry, since we need to be able to access the geometry function calls, or actually we need to be able to pass the cylinder as a geometry object so that the scene graph can handle this the same way that we've handled our existing objects, our box and our flat grid. Our constructor takes in those 3 parameters I talked about earlier: number of sides, radius, and height. Destructor doesn't take any parameters. We have to have an update and we have to have a render OpenGL. Remember that if we go into geometry.h here, we've created these as virtual, pure virtual functions because they're equal to 0. And because of this, anytime we inherit from geometry, we need to implement these guys. If we don't, then the compiler is going to complain. So here we go. We have the update and we have the render OpenGL. Our member variables contain the number of sides, the radius, the height, as well as a pointer to vector 3 for the normals and a pointer to vertex 3 for the vertices. And inside the constructor, we're going to basically allocate memory for each of these according to however many sides the user wanted this cylinder to have. So let's save that, and now let's go into the CPP file. Okay, so at the top we have our include stdafx.h and geometry cylinder.h, and then we have our constructor. Now inside the constructor we get these 3 values and we do a little bit of checking here. We check to make sure that the number of sides is not less than 3. If it is, we automatically default the number of sides to be equal to 3. And this is because if the user specifies negative numbers, or for instance number of sides equals 2, we can't really work with that down inside this constructor, because a 2-sided cylinder isn't really a cylinder. It's not a 3D object, it's really a plane. So some of the math that we use down below will break down. So to avoid that, we automatically default anything less than 3 equal to 3, so that we create a triangular prism instead of a flat plane or something that would give us errors. If the number of sides is greater than 20, we automatically default to 20. Now the reason why I've done this is because you'll notice that when you start playing with cylinders, if you want them to look circular cross-sectionally, you want to have a large number of sides. However, the more number of sides you create a cylinder, the more vertices and the more data that this cylinder contains. And really, when you look at a 20-sided cylinder and compare it to, for instance, a 50-sided cylinder, you're really not going to be able to tell the difference in terms of how crisp the circular cross-section is. For games, most of the time you use relatively rough models. You don't try to use absolute exact models of geometries. Like for instance spheres, you're not going to create a sphere that has like a million triangles that define the sphere so you get a smooth surface. You'll notice in almost every game you play, you can see the faceted sides of a sphere because of the number of sides that are defined. Same thing here for the cylinder. I cap it at 20 because beyond 20 you're really adding more triangles to define the cylinder itself, but it's not giving you very much visual feedback to give you more smooth looking cylinder. And as a matter of fact, in the next video, I'll show you how to smooth out the cylinder to make it even look better than what we're going to implement here. So let's move along. After we do this correction for the number of sides, we then save the value inside of our member variable. We take the radius value that gets passed in here. If it's less than or equal to 0, this means it's invalid. We automatically convert it to be equal to 1 so that we have a valid radius value to work with. And then we take the radius value and we save it inside of our member variable. We do the same thing with height. If the user passes in some value less than or equal to 0, we automatically change it to 1 and save it inside of our member variable. So by this point, we now have our 3 values that we need to start creating our cylinder in memory. We set the pointers for the normals and the vertices equal to null, and then we call the new operator. Using the new, we need to define how many normals and how many vertices do we need to store. Well, looking back here inside PaintShop Pro, if the user specified to have a 4-sided cylinder, we need to figure out how many normals we need. Well, we know we're going to need 1 normal for every single side. So actually, let me go and draw where these guys are going to go. If we're to take this cylinder and look at it from the top view, we would have something that kind of looks like this. And from the top view, we can see we'll have a normal here, a normal here, a normal here, and a normal here. So we definitely need 4, which happens to be the number of sides. But that's not it. We actually need 2 more. We need the normal that defines the top surface. So this guy's going to be pointing straight up. He's going to be perpendicular to the top. And we need another one that's pointing straight down for the guy at the bottom. Now, if you look at this though, we can hard code this normal and this normal because we know that the geometry of the cylinder is always going to be sitting upright with respect to the coordinate axis we're using. And the one we're using in OpenGL is defined as follows. We have x to the right, y is straight up, and z is out of the screen. So we know that this normal here is always going to be 0, 1, 0, and this normal here will be 0, minus 1, and 0. The remaining 4 normals, the ones that define the perpendiculars to each of these faces here, are going to depend on how many sides the cylinder itself has. So those ones we need to calculate dynamically. And so that's what we do here. We define a new operator because we need to store vector 3s for each of the normals, and the number of normals we need is equal to the number of sides that the user has defined. The number of vertices that we need to store is equal to 2 times the number of sides. And again, if we go back into PaintShop Pro, let's take a look here. Where are the vertices? Well, I've labeled them already for you here. We have 0, 1, 2, 3, 4, 5, 6, 7. And because this is 0 base, we actually have 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8, which is 2 times the number of sides. And that's always going to be true. So here we go and allocate new memory to hold 2 times the number of sides of vertices, and that's going to be stored inside of our member variable. When the compiler goes through here, if both of these values return correctly, meaning they're not null, then we know we have allocated enough memory and we can continue on through. If this fails, then down below we have just some cleanup code so that this class doesn't chew up any memory. Okay, moving on. Next thing we do is we need to define what are the coordinates of each of those vertices. Well, we can do that automatically using the following for statement. We define 2 values, the x value and the z value. Looking back here, we can see that all the vertices on the bottom face here are going to have one value for y, and that value is actually going to be 0. And all the vertices up here are going to have 1 value for y, and that's going to be equal to h. So down here, all values of y, how can I do this? Let's just change the color here, and I'll write here all y equal to 0, and I'll here all y is equal to height. Okay, so all we really need to do is for each of these vertices calculate what is the x value. So this value here is going to be 0, 0, 0. This value in the center is going to be 0, h, 0. So this first vertex is going to be some value x, 0, and then some value z. And this guy here is going to have the same sort of deal, some value for x, some value for z, and the y value is going to be 0, and so on. So we need to calculate the x and z values for each of these guys, as well as each of these guys up above. So using these variables here, fxval and fzval, we calculate them automatically using this for loop. Now, the way we calculate them is we use the cosine and the sine values with some multipliers. The radius is the value that the user passes in, and we multiply by the cos value of minus I times 2 pi divided by I number of sides. What this does is it really takes the unit circle for the cosine and divides it up by the number of sides and gives us the appropriate coordinate for the x value. We do the same thing using the sine to get the z value. And if you're familiar with regular trigonometry, you'll be able to figure out how this works. But really, all I'm doing is back here, let's see. If we're looking at this item from the top, the unit circle, I don't know if I can draw this nicely, but the unit circle looks something like this from the top view. And you'll remember that any point along the unit circle is equal to cos theta sine theta. And if we want to change the radius of this, all we need to do is multiply by r. So we now have r cos theta and r sine theta. So this will give you the x and the y value. Well, for us, it's the x and the z value. So for the x value, we have r times cos theta. And theta varies from 0, this is pointing straight horizontally, to, if you go a full 360 degrees, that's equivalent to 2 pi radians. Well, we have to stop at a certain number of points along this unit circle. And the number of points is defined by the number of sides that was given by the user here. So what we can do is take this 2 pi, which is the full circle, divided by number of sides. So this will give us each section. So if we take 2 pi and divide it by 4, we get pi over 2. And pi over 2 is 90 degrees. So we're going to start here at 0. We're rotating 90 degrees, so we end up going straight down to here. And then we take the next 90, and then the next 90. Now, you may be wondering why I'm counting everything here clockwise, when in reality, the sine and cosine always calculate things counterclockwise. And that's because, if you look at the code here, I'm using a minus here. So I'm taking the minus of the value here from the for loop, which makes our rotation inside this guy go clockwise. Normally, we would go counterclockwise. Now, because we have this factor here, 2 pi divided by number of sides, that tells us how much to move. And we need to multiply this by a factor, which I call I, that goes from 0 to 0 to number of sides. So looking back here, we'll start to here, and we'll go 0 times this, so we get this first value. Then I is going to be 1, so we get 1 times 2 pi over number of sides, so we get 90 degrees. Then we get 2 of those, so we get 180 degrees, and then we get 3 of those, which is 270 degrees. So that's basically the math involved to get all the coordinates for the bottom face. Once we have this fx value and fz value, we need to save them, and we save both the top face and the bottom face at the same time. The bottom face is going to be indexed from 0 to I number of sides minus 1, so it's going to be 0 to 3. And as I said before, all the y values at the bottom face is equal to 0. At the same time, we can save the coordinates for the top face as well, just by taking the I plus the number of sides here to index the top face's vertices. And here, the only difference is the height value is implemented for the y value. So here, instead of 0, we have f height. And we're using the same x and the same z value that was calculated up above. So going through this, we save all the vertices for the top and bottom face of our cylinder. Then the last thing we need to do is calculate the normal for each of the faces for the column part of the cylinder. Now when I say column part, what I really mean is for this section here, not the top face, not the bottom face. Because as I said before, the top face, we already know that the normal is going to be 0, 1, 0, and the bottom face's normal is going to be 0, minus 1, 0. So we don't need to calculate those. Those are always fixed. The only ones we need to calculate are these normals here that are representative of each of the sides. Alright, how do we do that? Well, again, we go into a for loop from 0 to I number of sides, minus 1 because this has to be less than, and we calculate the normal according to the following. Normally, we're going to be inside of this else, except for the very last side, and in that case we're going to be using this statement up here. I notice we're missing a bracket. It's somehow got way over there, so let's just correct that. Alright, let's take a look at this one first. What we're doing is we're using the plane class which we created in the last VMK, and this is where it becomes handy, because if we didn't have this plane class, we would have to implement all this math ourselves every time through the loop. But because we have this plane class, we might as well take use of it. What we do is we take 3 coordinates from the vertices that were calculated up above, and the 3 coordinates we use are n plus I sides, n, and n plus 1. Using those 3 vertices, we define a plane, and then once we have a plane, we can just go and call the getNormal function from that plane class, and it's going to return the normal for a specific value. And that guy is going to get saved into our member variable that contains all of our normals. And then we continue on through. The only difference is for this last side, because of the way we handle these indices, we need to hard code that we need to use number 0 here. You'll notice n plus I sides is the same here, n plus I sides, n is the same here, but instead of n plus 1, we use 0 here. Why is that? Well, let's go back into PaintShop Pro and take a look what this here is doing. We're going to start off at normal number 0. And normal number 0 is going to get defined as this side right here. Man, it looks like I'm running out of colors here. Let's use black for the normals. Well, actually, I used red here before, so let's go back to red for the normals. Okay, on this first section here, this guy will be N0. This guy here will be N1. This guy here will be N2. And this last one is N3. So, to define N0, what we need to do is define the plane that defines this one side of the cylinder. Well, to define a plane, as we said before, we need either a normal and a point, or 3 points. And because we're trying to calculate the normal, we're stuck with having to define the plane using 3 points. Well, we already have 3 points. We actually have 4. We have this vertex here, number 5, number 4, number 1, and number 0. So we can choose which 3 we want to use. And the 3 that I've chosen is the following. So when we're defining this one, we're going to take this guy, and this guy. And as a matter of fact, the order does matter. So make sure you choose them in the same order. So we start off at I equal to 0. So when we have I equal to 0, that means we need to take I plus num sides, which defines this guy up here, which is basically 0 plus 4. Then we take the index at I, which is this guy here. That's the second one. And finally, we take this guy here, which is I plus 1. Those are the 3 coordinates. Given those 3, we pass them into the plane class, and then we return the normal for that plane. We increment I to be 1, and then we repeat the process. So now, when we're calculating this normal, we need vertex number 5, number 1, and number 2. So if I is equal to 1, we have 1 plus 4, which is 5, we have 1, and then we have 1 plus 1, which is 2. So that's how we get those guys. And we repeat the process for this guy and for this guy. But notice what happens with N3. When we use N3, we have I equal to 3. And if we didn't change the code, we would have a problem, because the code works as following. We take I plus number of sides, so we have 3 plus 4, which is 7. So we take this guy as our first coordinate. We then take the second guy as equal to I, so that would be vertex number 3, which is this guy here. And then we have, okay, we need I plus 1, so we need vertex number 3 plus 1, which is 4. Well, number 4 happens to be up here, but that's not the one we wanted. We wanted this one here. So that's why we have to hard code that for the last plane, we need to take this guy, and V0. And the reason why this comes up is because, as you notice here, we have 0, 1, 2, 3, but this bottom face wraps around to the beginning. So we have to use this coordinate V0 twice. And as a matter of fact, we also have to use V4 twice, but that doesn't show up because the way we've chosen our plane definition. We're only using this guy twice. This is important to understand, and it gets even more confusing whenever I introduce texture coordinates in the following videos. So try to get this straight in your head, that there's a number of coordinates, but some of them are used more than once for specific faces. Like for this face here, we're using 0, 1, 5, 4. For this face here, we're using 1, 2, 6, 5, and so on. And we can go around, but then when we get to the last one, we're using 0, 3, 7, 4. And 4 is used twice because it's used for this one and for this one. So every vertex is used twice for every single side of the column here, as well as for the top and the bottom. We reuse these vertices. We don't want to create extra vertices that define this plane. I mean, we could, but that would just be a waste of memory, because we have all the geometry we need to be extracted from just the number of sides times 2 for all the vertices. Alright, now that I've confused you, let's go back into C++. Okay, so that's what we're doing here, and if I just scroll across this side, we're just taking the x, y, and z values extracted from each of those vertices, plugging them into vector 3, which is then plugging directly into the plane. Okay, so after that, this calculates, the top part calculates the vertices, the bottom part here calculates the normal, and then we're done. Well, we're done with the constructor, that is. If this part here failed on us, then we need to go down in here into this else, and we call safe delete array m underscore n, and safe delete array m underscore v. Now, it could have failed because of either of these, so that's why I call both. Really, you don't need to call the first one, but I just do it for cleanliness. We have our destructor, which just calls safe delete for both of these. We have our update, which doesn't do anything, similar to the other geometries that we've created. And then we have a render. Now, the render is a little bit interesting because we've defined it to have textures. Well, in this video, I'm not going to show you how to implement textures yet, because I think it's confusing enough as it is without implementing textures. I'll put the textures into the following videos, but for now, let's just put a cylinder on the screen with no textures. So, if textured, right now this is blank. We're going to implement this in a future video. Else, we're not using textures. here's what we do. We first have to break down our cylinder into 3 renders. We render the column section, we render the top section, and we render the bottom section. And each of these are done separately. So to render the column section, we go into a for loop, and we go from 0 to mi number of sides. We go one at a time through here, and each time through we define a GL quad. And GL quad is basically a way to call OpenGL function calls so that we're saying, here are 4 vertices, render them on the screen. Thing is, those 4 vertices you define have to be planar. And because they're planar, that means all of them lay in the same plane. Because the way that our constructor works, this is not a problem for us because all the vertices will be defined in a plane. Before we call GL vertex 3f, we need to call GL normal 3f to specify the normal for each of these faces that these quads are going to represent. And we already have the normal stored, so all we're doing is extracting the normal from m_n, the x, the y, and the z value. We then go, and depending on what the v value here is, we define the first 2 vertices that represent the side of this, the specific section that we're trying to render. So we're either going to be using the vertex 0 and m_i number sides, or v plus 1 and v plus 1 plus I number of sides. Now what's the difference here? Well, we have this if statement here for the same reason we had the if statement up here, because of that overlapping section. So if we scroll back down here, we have 0 and I number of sides for adjusting the coordinates at the seam where we wrap around to the start. And again, we're just taking the x, y, and z values for each of these. And then because each quad has to have 4 vertices, we define 2 here, and the other 2 are always going to be the same. It doesn't matter if we're on the seam or not. And we're taking v plus I number of sides and the equivalent value for v. Now I notice here that some of my spacing is off a little. Let's just fix that up a bit. Like so. Just a little bit easier to read. And there we go. And then we call GL end. So that defines each of the flat sections of the columns, and then we have to render the top cap and render the bottom cap. The top cap we call GL polygon, and the way this guy works is we call GL vertex 3f for each of the vertices that define the top face. But before we do that, again, we call GL normal 3f, and here we go. We've hard-coded the 0, 1, 0, because as I said before, all the vertices for the top face have a normal value of 0, 1, 0. All the vertices on the bottom face have a normal value of 0, minus 1, 0. So going back into here, we see we've set the normal, and then the vertices are defined as just taking the v value plus I number of sides, because these are all the ones on the top face. So we take the x, the y, and the z value, and we go through all of them for the top face in called GL end, and then we do the same thing with the bottom cap, but this time we use -1 for the bottom face is normal, and we call x, y, and z, this time only for the v value from this for loop. Now notice one thing here that's important that I had a little bit of difficulty with because I forgot to do this properly the first time around, and that is, notice this for loop. This for loop here goes from 0 to I number of sides, and it increments by 1. However, this bottom one goes from I number of sides minus 1 down to 0, and we decrement by 1 every time. The reason why we do this is because when we implement texture coordinates, if you don't reverse the order in which you define these vertices, you will end up with the wrong face pointing outward. So you may notice that you have like an open cylinder, for instance, from one side. So to fix this, you have to make sure you have the right culling of the counterclockwise ordering of your vertices for your faces. And to do this, the top face always has to be positive, the bottom face will have to be negative here. If you don't do this with this ordering, then you'll notice that one of your faces is missing on the cylinder. Okay? And then that's it. So that completes the geometry cylinder class. Let's go and compile this. Make sure I didn't create any errors, and we didn't. That's good. And now we can just quickly go into our scene and implement one of these cylinders. Geometry cylinder scene. We want to go inside initialize. Let's see, loading geometry. Okay, we'll create a new geometry here. Geometry cylinder. P cylinder equals new. And we define the number of sides. So, I don't know, let's pick 7. Radius, let's pick 0.25 maybe. And the height, let's say 0.5. I'm just picking some numbers off the top of my head here. If not P cylinder, then we generate an error message saying that there isn't enough memory. Else, we need to go and save the cylinder. Okay, and then we need to place it inside of our scene. So let's go and create a new transform node, and we'll need to create a new shape one as well. So at the bottom here, let's go call new transform node. This new transform, we don't need a name, we don't need any rotations. Let's just move it. Where shall we put the cylinder? Let's do 0 in the X, 0 in the Y, and we'll push it to minus, I don't know, let's say 6. And we'll put it straight in the root, so we can do that. And then we're going to create a new shape. This time we're going to call P cylinder here. And we want to add this shape to this guy, so that's fine. And we're not going to assign a texture to this just yet. We'll do that in the following video. So let's save that and go and compile this. And it looks like I forgot something here. Oh, right. Scene.cpp doesn't know what a cylinder is because we just implemented this, which means inside a .h file here, we need to go and call include like so. Alright. And now let's run this and take a look. And there we go. We have our cylinder, our 7-sided cylinder, which we see. And you'll notice that the cylinder itself looks relatively sharp. And the reasons for that is because we haven't smoothed anything out. As a matter of fact, in the next video, I'm going to show you how to smooth out the cylinder. And then in the following video, we're going to implement textures. So if that cylinder itself is a little bit too sharp, for now what we can do is just crank up the number of sides. And as soon as we do that, you'll notice that the cylinder looks a little bit smoother because there's more edges to it. So there we go. The cylinder itself is looking much smoother now and a lot more round as well. But each of the sides are still very sharp, you could say, because they're what we call faceted in the 3D industry. In the next video, I'm going to show you how to smooth out each of these sides so that it looks a lot more like a circle or a spherical cylinder without actually having to add so many faces. And you'll notice now, if we were to crank this up to like 100 or whatever, 1,000, it still looks exactly the same because we've hard-coded inside here the limit for the 20 up here. So if you do want to go higher than 20, you're going to have to change this limit here to whatever you want. However, in the next video, once I introduce the smoothing, you won't have to go higher than 20 to get a smooth-looking cylinder. Okay, so I hope you understand this video. It's the basics for the cylinder. In the next video, we're going to go introduce smoothing to the normals so that the edges of the cylinder itself look a lot cleaner. And then in the following video, we're going to introduce textures so that we can actually make use of the cylinder to have some neat things like, well, I won't tell you what I'm going to do with it yet. Come back for the video and take a look. Okay, so if you have any questions, come check out the website. As soon as I finish posting this video, inside the community section here, you'll notice that I'll add a new forum discussion for the cylinder where you can post questions about specific issues that you may be having with the cylinder class.